Just give me 45 minutes. 45 minutes is all I ask for. Right, so let's get going. I would like to finish this one in about 20, 25 minutes and move on to the next topic. Okay. So, hey, I'm still here. I'm still here. I've only just started. Right, so we were discussing how to find the maximum load we can apply to a structure to ensure that it doesn't buckle. Okay, so where we mean that it doesn't go that way. So that's what we've been doing, and we've discussed how to obtain that critical load when the ends of the structure are both one end is pinned and the other end is pinned as well. And now we have just started on Tuesday. What happened if one end is fixed and the other end is free? So, and that's where we were, and we went as far as obtaining the solution of the load for a case where one end is fixed and the other end is free. And that is the page where we stopped. So this is where I'm going to continue. So we're going to go now and look at what happened when both ends are fixed. So what happened when one end is fixed and the other end is pinned. So we'll go through that, and then we'll do the two simple examples at the end. I think I've only got two. Yes, I've only got two there. So we've already derived that. So the solution we obtained, the one which I've given in 4.13, and there are different modes. So when n is 1, and n is 3, and n is 5, because the load will slowly increase from 0 to a particular critical value. So failure will occur at the minimum possible value of P, and that is when n equals 1. So when n equals 1 is the one that will happen first before the rest. So in design, we therefore base our design on the value of the load when n equals 1. And so which means we can determine the maximum load that we can apply, which is given by that. If you go above that load, then that structure will go that way. So which is what we don't want. So, but we can also use that and write it in terms of what we call the slenderness ratio, which I explained on Tuesday. If you recall, I'll put here. So recall that our radius of gyration R is the square root of I over the area of the cross section raised to power 2. So if we are to do that, so we can find that critical load in terms of the surface area, and so therefore we'll be able to determine whether the failure is likely to take place. Sometimes we are also interested in the actual shape. So what is the deformed shape of the structure, and the deformed shape of the structure which we showed. Let's move that down there. So that is the one that we showed here. We know C1, we know C2, and we can put those ones in. So I will just put that here. So note that we've already derived that. We've already shown that C1 is 0, and we've shown that C2 is minus delta. And if we put that in that equation, we'll be able to obtain that deformed shape. And I will show what that deformed shape will look like. So my next slide shows what it will look like if it does actually buckle. So if that structure does buckle, so that's what the deformed shape will look like. So the first one is the first mode, which is the most likely to take place. I will call that is the mode 1 when n equals 1. And that is the mode 2 when n equals 3. And that is mode 3 when n equals 5. So the first one is the one that has the minimum magnitude of the load, and which is the one that is most likely to take place there. So what happens if the structure has both ends fixed, or one end fixed and one end pinned, and you can keep going on for the different boundary conditions. So we're not going to go through all the solutions. What I need to show now, I'll show you that the general form of the critical load is very, very similar. So sorry for that ink there. So we just go through the same process. So we determine the bending moment. We set up the differential equation, which we've shown twice now. we obtain the general solution for the deflection, we apply our boundary condition, and then we'll solve to find the actual critical load. So those are the steps that we need to go through. And we've already shown what happens if it is pin. So that's the first one that we did. And the one that we've just done is a fixed end and one end free. So, and then the one which I'm going to show very shortly is what if one end is fixed and the other one is pinned. And then the last one is what if both ends are fixed. So we've obtained that, and we've already obtained that just now. So, and we'll be showing what the solution will be look like for fixed and pin, and then fixed and fixed, without any derivation. But I will show what the solution will look like. Right. So let's. Oh, who's that? Right, so let's quickly go on. So whoever's talking, please. So now that we have the solution for the case where both ends are pinned and when one end is fixed and the other one is free, we want to go through how we obtain the rest without going through all the derivations. So in order to do that, we want to introduce what is called the concept of effective length. That will allow us to just write one simple equation that we can use for all cases there. So the concept of effective length, so which is there, is the length between the points with zero bending moment. So if I move that up, you might be able to see that. So here is a vertical structure which is pinned, that is pinned, and that is pinned. If it is pinned, there is no constraint on the rotation there. So which means at this point, there will be no moment. And you've already done that in your first tutorial. And here, there is no moment. So there is no reaction moment at those points because it is pinned. But you will have reaction forces, but no moment at all because that structure is able to rotate freely at that point. So for structure where both ends are pinned, therefore my effective length, because it's defined as the length between 2 points with zero moments. So my effective length is effectively between this point and that point. Are you asking me a question? No, okay. So if we go to the second one, which is the one we've just done, where one end is fixed and the other one is free. So because this end is fixed, it will have some moment. So this will have reaction force and also will have reaction moment. So that location there will not have zero moment. It will have some magnitude of moment because it is fixed at that point. So the beam is not free, or that column is not free to rotate at that point because it is fixed. But the end there is free. So therefore, it has no moment there. So if I ask myself, what is the effective length of that? Remember, effective length in this case, the distance between 2 points, which have got no bending moment at all. So for that one, we know that one has got bending moment. That is free. The only way I can get effective length is to assume. So is to assume I have that second part of it going downwards, where that is fixed. That is also free. So I will say that one here is free. So it's got no moment at all. So my effective length for a beam, for a column with one fixed end and one free end, is from here to here, which is 2 times whatever length that you've got there. And we can do the same thing for the rest of the different boundary conditions. So if you go back, therefore, we can just write our critical load in terms of our effective length. All I need to know now is what is the effective length for different cases. Yeah.
So when it's free and when it's fixed, it's what? The moment of the sentence, when it's free and when it's fixed.
So if you have a structure that is fixed
Fixed on the free
end,
yeah.
so
Both of them have no moment.
no. You always have moment where it is fixed. Because if you fix a structure, you are stopping it from moving and from rotating. So therefore, you will develop a reaction moment at that point, and you will develop a reaction force at that point. So for this one here, which is fixed at this point, that particular structure is not free to rotate at all at that point because it is fixed. So therefore, you will develop a reaction moment, and you will develop a reaction force. So at this location, you don't have zero moment. You have a magnitude of moment. At the other end, which is free, there is no constraint. That column can rotate freely at that at the top, but not at the base.
Okay, and also no force, reaction force on the top.
Which one? This one?
On the top, yeah.
Yeah. So that force is the load you are applying to the structure.
So we have force.
Yeah.
We have reaction force.
Yeah. Here. Yeah. So it's not reaction force. It's the force you are putting on the structure.
Okay, so no reaction force.
No. So when you
Force applied.
yeah. So when you use this term reaction,
Yeah.
you are referring to what is coming from the support. Okay? So there is no support here. That is the load you are applying. Okay? At this location here where you have support, you have reaction force. Is that clear? Difference between the load you apply and the load you are getting from the support. Okay, so now we can go and look at what the critical load would be without look. Yeah.
So for the second beam, that lower part,
Yeah.
does it have, how is it attached? Is it fixed, you said, right?
Yeah, yes. The second part is just an imaginary one to be able to find how long, what do we need to find one end with zero moment and the other end with zero moment.
But how can we picture that?
What do you mean?
Is it, if this is that beam, right?
No, this doesn't exist. Okay, this is your structure.
So do these two pictures, do they illustrate exactly the same beam?
Which one? This one?
Both of them.
This one?
Both of them.
You mean these two?
Yeah.
No, they are different. Maybe, right.
But he said it doesn't exist, so what do you mean by that?
Okay, maybe I really have to finish this. So let me just quickly go through this again. So if you look at the definition of our effective length, we want one single equation we can use to find the maximum load for all different cases. Right? So, and we introduce what we call our effective length. We want to find, if we got 2 points in that structure where both points have no moments at all. For the first one, where you have a structure where both ends are pinned, that structure is free to rotate at the pin. So there is no moment here, there's no moment here. It's very easy. Therefore, I know the distance between the 2 points with no bending moment. That is my effective length. If you go to the second one, where one end is fixed and the other one is free, the end that is free has no bending moment. But I have moment where it is fixed. So the length of that structure is not my effective length. Because effective length is the distance between 2 points with no bending moment. So I would then ask myself, is there any way I can look at that structure and find what the effective length would be? And the way to do that is to say, if you have a second half of this, just imagine you have a second half of that, where this end is free and that end is free. Although it is fixed here, these two ends here will have no bending moment. Therefore, our effective length is the distance between this point and that point. So therefore, I would say the effective length is 2 times the original length that I've got for that particular structure. Okay, so I hope that's clear. You will see when I do the two cases at the end there. So now I can write my main critical load in terms of that parameter called the effective length, which I will show next on the next slide. So now what we now have are all the four common cases. So the first one is the one we've started with, which both ends are pinned. Second one is where one end is fixed, the other one is free. And the third one is where both ends are fixed. And the third one is one end is fixed and the other one is pinned. So now you can see what the effective length is. For the first one, effective length is just the length. Second one, effective length is 2 times the length. Effective length here is half the length. And the other one is nearly 0.7 times the length there. So that is all I need to know. So in order to find the particular critical load, all I need to then use is just that, provided I know what is the effective length. So I've got E, Young's modulus. I've got I, second moment of area. I've got LE, which is my effective length. So if I'm dealing with a structure with both ends fixed, I know my effective length is just the length. If I'm dealing with a structure with one end fixed, other one free, my effective length here is 2 times the length. And if I'm dealing with this, my effective length is half the length, and I just keep going on like that. So that is all, and the only thing we have to remember is just that, and I'm going to show where it is in the formula sheet. I'm going to put this up again so that we all see that. That's the formula equation, which is basically what we've just done. We've just shown that. So now let me go through how to use it, and that might make it a bit more clear if I can find the example. So I'm going to use this first one, very simple. So you got an I-beam, which is standing vertical. It is pinned at both ends. It's there to support some load. So the load is coming from the top. So it is there to carry some load. I'll call that load P. And we are asked to find what is the maximum load you can put on that vertical structure to make sure that it doesn't buckle and it doesn't yield. Okay, it doesn't buckle, it doesn't yield. There are two failure modes. So I'll put that here so that we know no buckling and no yielding. So, and we start from what we know. We say, okay, for the first one to occur, the critical load will be pi squared EI all over LE squared. So that's where I'll start. So I want to check how high, what is be the load that I will need to actually make it to buckle. So the modulus we are given, so and because it is pin, so because the end are pinned, therefore the effective length is just the length of the beam, which is 4 meters of that structure. So the second one, so modulus is known, but that column can buckle about YY, and it can buckle about SX. So we calculate the load required to buckle about YY axis, and we calculate the load required to buckle about the second one. And the one that is likely to occur is the one that's got the lower value of load. So I'm going to do the first one. I'm going to find what is the critical load if the buckling is occurring about the first axis, which is denoted by that XX. So all I need to do is just substitute. So I've got pi squared. My modulus is given as 200 gigapascal. I will say times 200 times 10 to the power 9. That is in Newton per meter squared. My I for buckling about X, that is I will use IX, which is 46 times 10 to the power minus 6 meter 4. And then I will divide by the length L4, which is 4 squared. So if I was to calculate that, what I will get is about 5.675 meganewton. That is 10 to the power 6 of Newton. And then we go and do the second one, because we want to find what load will be required for it to buckle about the second given axis. So the critical load for buckling about y will be pi squared times 200 times 10 to the power 9. Then the moment of inertia about y-axis, which is given as 15 times 10 to the power minus 6, divided by 4 squared. So we get that, and that will give me roughly about 1.851 meganewton. So you need to be aware of units here. So if you note there, I've put that, my modulus is in Newton per meter squared. My I has to be in meter raised to power 4. And the length has to be in meters. If you are putting your modulus in Newton per millimeter squared, then your I has to be in millimeter raised to power 4, and the length has to be in millimeters. So the way I normally do it, I use standard SI unit, Newton meters throughout. So now we've got those two loads. It's very clear that the load required for it to buckle about YY is less than the one to buckle about SX. So if this is going to buckle, it's going to buckle about that. So I will say, so the critical buckling load is P critical Y, which is 1.851 meganewton. Because it is lower. So as you slowly increase your load, you're going to get to that one first before you get to the second one. But the question says that what is the maximum load you can apply to make sure that it doesn't yield? Because this can fail by yielding before it actually buckles. So we go back and we want to check whether that critical stress will give us, that critical load there, whether it will give us a stress that will exceed the yield stress of the particular material that you are using. So let's do that. So we're going to find what is the critical stress when it buckles. That will be the critical load all over the cross-sectional area. Yeah.
Excuse me, can you say it again? Why did you choose the load over y-axis, why not x-axis?
Because the one for x-axis is much greater. So when you are applying your load slowly, okay, if you're applying your load slowly, so you get to the lower one first before you get to the one above. So if it's going to fail, it will fail very, very early here. You will never get here because you will have reached this point well before you get here. And when you reach here, it will have failed. Yeah? That's if you are testing, if you are doing your lab, your test in the lab, the test you did for in first year, you slowly increase the load. So as the load goes up, it fails as soon as it gets to the first failure load. And the first failure load here is this one. Right, so now we want to find what the stress would be if it buckles at that point. We divide by the area of the cross-section. So the area we are talking about is the area of the cross-section of that I-beam. And we've already, I think we are given what that is. We are given the value there. If I divide by that area, what I will be doing now, I will say that is 1.851 times 10 to the power 6 divided by 59 times 10 to the power minus 4 in meters raised to the power 4. If we were to calculate that, we will get critical load of 3.7 megapascal. So, but my yield stress, the yield stress is given as 250 megapascal. So will that structure fail by yielding, or it will fail by the second failure mode that we are trying to find here? So the stress when it buckles, will be 313 megapascal, and the yield stress is 250. So in this case, what we have here, so that structure will not buckle, but it will fail by yielding. So because that is greater than your yield stress, failure is by yielding. because you will never get to 313 megapascal. You will get to 250 megapascal first before you get to 313. Therefore, it will fail by the second mode there. So if you are designing this, if you are trying to use this for your structure, what you then need is to find what is the load you can put in to make sure that you do not get to 250 megapascal. So, and that is the maximum load you can use. So I'm going to do the second one, which is slightly different. The second one is also an I-beam. Hey, who is that? I can't even hear myself. Right, so the second one is slightly different, but it's also an I-beam. So it's got a length of 8 meters, but it's also got some support. So that length there is 8 meters. It's got support halfway through, so which is 4 meters long. And that support is to provide additional reinforcement about buckling about two axes. So what the support is doing is to reinforce that direction there. So you put in some support to make sure that if you want to buckle about two axes, you have a bit of support there. And we are asked to find what is the maximum load we can put in, so to ensure that it doesn't buckle and it doesn't yield as well. So it's an I-beam. We've been given the second moment of area about 1,1 and about 2,2, and then we've been given the total area of the cross section as well. We go through the same thing as well. So this is also a case where both ends are pinned. So I'm going to look at the first one. The first one is right. Is somebody going to come here and come and talk? No, you're not supposed to talk when I'm talking. If you want to ask question, you put your hand. Sorry? Yeah, but you just ask me, because if you are talking, there are other people who are trying to listen. That is simple. It's simple, because other people are trying to listen at the same time. Just ask me. Or if they want to talk to your friend, you wait until we finish the class, because other people can't hear what I'm trying to say. Right, so we've got this I-beam. So for it to actually buckle about 1,1, there is no other support. So to buckle about 1,1, it will buckle over the whole length. To buckle about 2,2, because we have additional pin here that is providing additional support, the actual length that it will buckle will be between those two points. So we'll start and look at what load is required to buckle about 1,1 axis. So both ends are pinned. I'm going to start and write what is the critical load. Critical load is pi squared EI all over LE squared. So we know that both ends are pinned. Because both ends are pinned, so it is pinned. So therefore, our effective length is the length of the structure. So we look at the first one. So how to buckle about 1,1. So for buckling about 1,1 axis, we say P critical for 1 is pi squared E I for 1 all over the length of the structure. So we are given all of that. We know E, we know I about 1,1, we know the length, which should be from A to C, because there is no support to prevent buckling about 1,1 there. So we just make the substitution. So it will be pi squared. E is given as 200 gigapascal. That is 200 times 10 to the power 9. Then I for 1 is 3,060 times 10 to the power minus 6, all over L, which is 8 meters. Sorry, that's L squared. 8 squared. So if we were to do that, so remember, in terms of the units, the modulus have been put in as Newton per meter squared, I has been put in as meter raised to power 4, and the length has been put in as meters. So if you did that, we will get the load required for it to buckle about 1 axis will be about 943.8 kilonewton. So if you are below that load, it means that it will not buckle about 1. Yeah.
Can you just explain briefly what do you mean by buckling? Like, what will happen to the beam? That's all.
Yeah. And
So
so,
if it's buckling x-axis, that's what happens.
yeah,
And for y-axis, the opposite.
it will be like this.
Yeah.
Okay.
Thank you.
Yeah. Right. So,
How would the yielding look like then?
sorry.
How would the yielding look like?
Yielding is similar to what you did in your first year test, but instead of tension, you basically compress. So therefore, locally, it will start to yield, and then where it starts to yield, that deformation will become very, very unstable. So yeah.
So it starts yielding, it will be like slice deformation.
Yeah, yeah. So when you are designing, you will say in third year, you design to avoid yielding, because once your structure starts to yield, it's difficult to control the load sometimes. So
We're designing, we are trying to make the buckling like a PCR less than the yielding.
yeah, but what you want the load you are applying when you are using the structure to be less than that one, and to also be less than the load that will cause yielding, because you don't want yielding and you don't want that one as well.
So that we need that one to be more than yielding, and at the same time we have to design the structure to be applied for a force that will not cause the yielding at the same time.
Yeah, there's nothing that says you have to make this more than the yielding. What you are trying to check is, you know the load you want to put on your structure, and you're asking the question, is the load you are putting on your structure high enough to cause yielding? And is it high enough to cause this type of failure? You don't want buckling, you don't want yielding, you don't want fracture. So you check the load that will cause fracture, that will cause yielding, that will cause this. Every failure that you think could take place, you work out what load will cause them, and you make sure that whatever load you put on your structure is below every single one of them. Okay. So we do the second one, the load that will cause the buckling about 2. So we have pi squared E I about 2L squared is that. So now I'll do that again. I'll have pi squared times 200 times 10 to the power 9 times I2, which is 162, times 10 to the power minus 6. So now my length is not the full length of that, because of the pin support that you have there. So that is being supported about to stop the buckling about 2. So the length is between this point and that point now. So that we've got. We now have 4 squared. So now we have 2 sections. That is pin, and that top is also pin. So we're only looking at the one at the top. So now if you to do that, you will get a load which is roughly about 200 kilonewton. So if this is going to actually buckle, if it's going to buckle, it means that it will buckle about 2, because the load there is much less. So, but now we want to check whether that is high enough to cause failure by nonlinear plastic deformation, which is yielding. So,
Excuse me.
yeah.
For the first part,
Yeah.
when we are calculating the load
Yeah.
at the axis 1,
Yeah.
so the vertical, why didn't we choose 4 meters in that case and 8 meters in the second one?
Yeah, because if you look at how the reinforcement is, that's why the diagram is here. So for for the buckling about 1-1, there is nothing that is stopping it along the length.
So could you repeat that sentence?
So if I have, yeah, so if you have that, so like that, so that support that you have there, the support is about here. So if the support is here, in order for this to buckle like that, so I've got additional support here. The only effective length is this.
Are you talking about section one?
Yeah, no, 2-2. Yeah, 2-2 for now. But if you want to buckle this way, if you want to buckle that way, it's difficult to show here.
Yeah.
Okay, there is no support here. There's no support here. So the whole length here is needed because it's this end and that end, and it's going all over the length. But if I'm going this way, and I put support here, when it buckles, it's going to buckle between this end and that end.
So 1-1 is this sort of movement.
Yeah, so,
Not 2-2 is this movement, and 1-1 is that movement.
correct.
So it's not about like the point, like the actual axis, y and x. It's just about the point.
No, I'm not sure which point you're referring to now.
Because 2-2
Yeah,
sort of creates the y-axis, and 1-1 creates x-axis.
yeah.
I can't picture that how we chose that the length would be equal 4 and 8.
Yeah. Look,
in particular.
if you look at that and you look at that,
Yeah.
okay, that is being provided additional support, and that support is going here.
Yeah.
Okay, if that support is going there, all right in the middle. So if that structure want to bend, if you want to bend round,
Left to right.
yeah, like that. If you want to bend like that, then this is providing pin support. So if you want to bend, it's going to bend between this end and that end, and between this end and that end. So it's not going to bend all over the length because this is stopping it at the center. So what you cannot have this to do this. It's not going to do that because you got this here. So that is going to stop it. What you're going to get instead is something that will do this.
Okay, I understand.
Yeah. Okay. So now we do what is stress. I put whatever area we've been given the area to be 39.5 10 to the power -4 meters squared. If you put the value of the area, we will get the stress to be 50.6 megapascal. So the stress that we will get in that particular structure when it buckles, if at all it does buckle, will be that stress. But our yield stress we are given the yield stress as 250 megapascal. So in this case, unlike the first one, because the stress when it buckles is much less than the yield stress, if this is going to fail, so failure will be by because you will get to 50 megapascal first before you get to 250. So what you now want, if you are trying to design this, you want to therefore make sure that you know your yield stress is very high. So you're never going to get there with this load. You make sure that you apply a load which is just slightly less than 200 kilonewton. If you go below 200 kilonewton, you know it's not going to buckle because you need 200 kilonewton for it to buckle, and it's never going to yield. So we put something that is below that. Okay.
And if the second moment area for both axes would be the same,
Yeah.
adding additional support would increase the maximum load that we can apply before the buckle.
Yeah.
Okay.
Yeah. But there is a different way which I'm going to show. I'm going to show now. So how to do that? If you recall, I put this up right at the start of this particular topic. So you can see here where you have vertical columns like that. So you have all those vertical columns there. So if you calculate the load required to support a particular weight, and you think that that column that you have is likely to fail, either by yielding or buckling, then the question you might ask yourself is that I need to support this weight. Is there any other way I can do that? One, you can go back and say, I want to change the material. You have different modulus. I want to make the cross-section bigger. You increase I, or you want to make the length shorter. But if none of those is actually possible, then you can add additional structure. So instead of having one vertical column taking all the load, you have 3 or 4 or 5, and they will basically share the load. So I'll put a rough sketch here. So if you have that, therefore, what you now have is that whatever this weight is, provided these are all arranged in a symmetric manner, only 1/3 of this is taken by this, only 1/3 is taken by that, only 1/3 is taken by that. And with that, you can ensure that your design is a safe one. So, okay, I think I finished this topic. So, but hey, after I finish this topic, we've not finished yet. I've got 5 minutes. So I'm going to. Are there any questions before I move on?
If you have a few spare minutes, can we go over questions from tutorial?
I will leave tutorial questions for tutorial classes. I'll be putting solutions to the first tutorial up tomorrow, but not the second one yet, because some people are still doing it.
Well, yeah, and it takes ages to do that.
To do which one? First one, second one?
Either. Like I finished the first one, but the second one.
Oh, good. Good for you. Some people haven't finished the first one.
But my point is, sometimes we do, like, I think I'm talking about every student, we just stuck with one little thing and we can't move forward. And the access to the answers can help us to understand that.
Yeah, but why don't you ask the tutor? There are 2 tutors.
Well, I did spend 1 hour, and for 30 minutes we were trying to solve the question, and
Yep.
it was not very.
Yep. Okay. Then come at 4 o'clock. The reason I'm saying is I don't want to be going through tutorial questions here. We've already done example problems. I'm a little bit concerned that we'll probably not finish this topic. We have three other topics to do. We have five more lectures. 3 lectures next week, 2 lectures in the last week. So hopefully we'll see how far we go. I'm going to put the solution of the first one up tomorrow. So if not today, so I'll put the first one up. At least you can see that one there. If you want to ask questions about the second one, then drop by my office. I'll put the solution of the second one up much later next week.
How many tutorials do we complete for the exam? Is it just 1 and 2?
Which exam? Oh, the test. It's just the first one.
Just the first one?
It's just the first one. So if you...
I thought it was the first 2.
No, the first 2 topics.
So tutorial 1 and 2. Okay.
No, just tutorial 1.
So tutorial 1 includes the first 2.
Okay. Right. Okay. If you have not seen the notice I put up this morning, then go and have a look. I put there the list of topics that we covered in the first 2 chapters that we went through, and every single one there, you can get questions in the class test on them. I'm not saying it's everything, but every single one there, you might get questions on them. So, and I've listed all of them there for you. Okay, so I don't have, I only got 4 minutes. It's not enough to start a new topic. We're going to start a new topic next week. I hope we're able to finish, but I'm not too sure now whether we'll be able to finish, because we only have 5 lectures. We have 3 more topics to go.
Can we run another online class if we are not?
Yeah. Okay, so see you all on Monday.